got the Dragon 6-ton capsule. Could you actually do a Mars mission with this sort of hardware? And I've looked at this pretty hard. I think you can, although the margins are tight. You would adopt what is called, I call the semi-direct plan. This was actually the plan adopted by Johnson Space Center in its design reference mission 3, which I think is their best designed reference mission. That was a 3-launch, I mean, they didn't use these particular elements, they were doing everything on a larger scale, but the flight architecture was this. 3 launches, 1 sends a half to Mars, and they initially sent a full habitat to the surface, but with no one in it. That gives them an extra half to start the sequence. They send an Earth return vehicle which goes into Mars orbit with enough fuel to kick out of a highly elliptical Mars orbit and shoot back to Earth from there, which is only a delta V of 1.5 kilometers a second. And then an unfueled descent vehicle which goes to the Martian surface and makes its return propellant much as we do in Mars Direct. So now you have a Mars ascent vehicle. This is a smaller vehicle, and it only has to go from the surface up to the highly elliptical orbit. So what this does is this does introduce a mission-critical Mars orbit rendezvous into the architecture, but it reduces the ISRU requirements by about a factor of 3, and therefore the power requirements by about a factor of 3. And given that you have a much smaller launch capacity than I would prefer, you really do need to go this way if you wanted to do the mission with this sort of flight hardware. And then we also have to reduce the crew to a crew of 2. Why 2? Wouldn't it be better to have 6? Yeah, it would, but you can't. Okay? So you go with what you can. And then you do the mission in this way, 3 launches every 2 years, each one sending a Earth return vehicle, a Mars ascent vehicle, and a surface pad. The Dragon would be a very small living space to fly from Earth to Mars in, so you would use an inflatable extender like this, and you can make artificial gravity spinning off of the trans-Mars injection stage, much as we do in Mars Direct. This thing could be deflated when you get to Mars and stowed back into the capsule, or you could simply discard it and inflate another one after you land. Oh, by the way, this is what I promised you. These are cosmic ray radiation doses received by a variety of astronauts and cosmonauts due to cumulative activity on the Mir or the ISS, or in some cases even the Saudi space stations. And these doses are quite comparable to that which you would get in either a well-designed or a poorly designed human Mars mission, and there have been no radiological casualties here. Okay. So the idea that, frankly, I got to tell you that NASA has, or parts of NASA, have been using the cosmic ray hazard as the way a 10-year-old uses a snowball. 3 inches of snow, we just can't go to school. I'd really like to, but it's much too dangerous. Too much radiation, we can't go, but don't work on it. Once we have warp drive, we will go.
What are the units on that chart?
Those supers?
No, these are REMs.
Oh, REMs.
Yes, 100 REMs is 1 super. Okay, and I've worked out the masses of this you know, Falcon-driven Mars semi-direct mission with a crew of 2, and this is, by the way, and it does work, assuming average-sized people.
Mm-hmm.
Now, it would be better to use small people. Now, I mean that. I frequently get a laugh when I suggest that, but I'm trying to make everything else small and lightweight on space missions. But when you say, you know, a 100-pound person uses half the fluid and oxygen of a 200-pound person.
Mm-hmm.
So that's something to think about. But these were actually assuming average-sized people, and it does work. So this is the sort of thing that could be done. I mean, my main